Right, so it's 14 and 57 minute, 14 degrees and 57 minutes, right, for a 15-degree arc. And then if you chop it in half again, you've got 7.5 degrees, and the degree measure of that chord is indistinguishable from the degree measure of the arc at the level of minutes, right? We have to go out to seconds to be able to distinguish those. Any questions about this?
Why did you add one of them and not the other one?
Sorry, which one, what?
You know how on the table it says 29 on 40?
Yeah.
That one's 29, but the other one's rounded to second. Okay, never mind.
Make sense?
Yeah.
Yeah. Right, so I waited until I converted to the nearest hundredth of a minute in order to do the rounding, because it's a pretty close call, right? So you want to wait, and then once you have enough evidence, do your rounding.
What's that second value under arcs? Like 15 and 0, what's the 0 represent exactly?
Minutes? Like ordinarily with our original sexagesimal notation, we'd have a semicolon between the degrees and the minutes. But here the semicolon is dropped and we just have a comma. Perhaps because it's, you know, clear in context. We're talking degrees, minutes. And so we can drop the semicolon and just have a comma.
So for the arc, 30 degrees, how does that return 0 minutes exactly?
This?
Yeah.
Well, that's an exact measure of 30 degrees. The chord is approximate, right? So all these arcs are exact, right? So 7.5 degrees, twice that is 15 degrees, twice that is 30 degrees, twice that is 60 degrees. And 90 degrees, how did we get 81.2?
Well, okay, so at 60 degrees, the one you just highlighted,
Yeah.
the second value is 0.
60 degrees and 0 minutes, so exactly 60 degrees.
Okay, versus 52 and 30, what's the difference? I'm sorry, I'm not sure what that second value has any.
Yeah, so this is minutes, right? So this is base 60, so this is 30 60ths, so this is half, 30 60ths is half of a degree. There's 60 minutes in a degree, so that the second, these are all sexagesimal numbers, but they're not using the semicolon notation.
Oh, they're just saying and a half.
Yeah.
That's what that is.
Yeah, yeah, so you
Okay.
can see these are all evenly spaced, 7.5 degrees, 15 degrees, 22.5 degrees, 30 degrees. So you just keep adding 7.5 degrees, right? And that's how this table is generated. So, so what is the degree measure of a 90-degree chord? So what do I mean by 90-degree chord? Draw a right angle here, right, 90 degrees. So then what is the radian measure of that chord? And radians are just pure numbers, right? So this is the radian measure of the radii.
1.62? Yeah, because that would be like half a pi, right? Because that would only stretch 1/3 of pi, right? The length of
I think
that.
for this you want to use Pythagoras' theorem. Right? So the length of AB here is going to be chord AB when squared is going to be the sum of the legs of the triangle, right? Right, so this is Pythagoras at work here.
1.5.
The square and the
1.57.
hypotenuse is the sum of the squares on the other two sides. And so that's going to be 2. That means that AB is equal to the square root of 2, the length of AB. And so sometimes I put the little mark over the top to indicate that it's a line segment, and sometimes I don't. This is sort of standard sloppiness in the business. If it's a chord, I'll put in, if it's an arc, I'll put in a curvy thing, right?
1.4.
But yeah, so the straight line indicates it's a chord, and the curvy thing indicates it's an arc. So,
1.04.
so how do we convert this to the degree measure? and we take the square root of 2 and multiply it by 180 degrees per pi radians, right? And that's going to give us what? Well, let's just do it on the calculator. Where's the calculator? Here. Okay, so I got square root of 2 times 180 divided by pi, and that's 81 2/2. Should I take a couple more digits? 284?
5.
285 if I round, yeah. And that's a degree measure, right?
Yeah.
So I want to say, okay, well, that's 285 10,000ths, right?
Yes.
And that's degrees. And I'm
Times
going to convert
180
that
over pi?
to minutes. If I can multiply
1
by
degree.
60 minutes equals 1 degree, right? That's the conversion factor from degrees to minutes. And what do I get? Well, 30, 48, 51, carry the 5, you got 17 here, and that's over
10,000.
10,000. So, is that right? Did I do that right?
Looks right. So
30.
it's 17 minutes? Or
I think
17
I need another 0 here for one thing.
Oh, so you need one
And
zero at the
then
bottom.
30, 48, 51,
Uh-huh.
carry the 5, 12, and 5 is 17, right? So, how many times does 10,000 go into that? Well, it looks like about 1.7 minutes, right? And if I were rounding that to the nearest minute, what would I get?
2 minutes?
Yeah. And so does that comport with my table? Here's 90.
2.
Yeah, so we got the 81 degrees and 2 minutes. All right, so that's the degree measure of a 90-degree chord. Right? A chord subtending a central angle of 90 degrees. Okay, and then you just keep doing these computations until you get to 180. What happens after 180? Well, think about what happens to the chord after 180. So let's redo this diagram with 48 sides. Is that where we're going with this? 48 sides, huh? A regular 48 guy? Yeah. Okay, so let's see if we can draw that reasonably well. So here's a straight angle, 180-degree angle.